Hello students, my name is Shashank Shekhar and today is the second class of the chapter Alcohol, Phenols and Ether. So in the previous class, we have seen the classification and your nomenclature of this alcohol. So today we will be basically focusing on methods on preparation, okay? Methods of preparation that are used to prepare alcohols. So today we will be doing this. So these are the topics that we will cover. So starting with the substrate that we can see or you can use for the preparation of alcohol. Then the methods that we can use, acid catalyzed hydration. Then we will see the mechanism of the acid catalyzed hydration. Then this hydroboration oxidation and its mechanism. Further, we have this reduction of aldehyde and ketone to get our alcohol. And then the reduction of this carboxylic acid and ester to get our alcohol. Then we can prepare the alcohol from Grignard reagent also. At last, we will see some examples. So let us start our today's class. The first one is, what are the substrates that can be used for the preparation of alcohol? The first one is alkene. So alkene means containing double bond simply. Then we have carbonyl compound, means the one which contains C double bond O. And from the Grignard reagent, that is RMgX. So these three substrates will be used for the preparation, which has our alkene, carbonyl, and your Grignard reagent. So first we will see of what are the methods that we can use for the preparation of alcohol from alkene. So the first one is acid catalyzed hydration. So if you just break down this term, acid catalyzed means we will catalyze this reaction using acid and you will do the hydration. Hydration, you must have heard this word. It is related to water. So if you are hydrating something, you are adding water to that. So what are we doing? Here we are adding water in the presence of acid, or we are hydrating it using acid as a catalyst. So alkenes react with water in presence of acid as catalyst to form alcohols. So here you can see, here is a reaction. So we have used an alkene here. The site substituents are not defined. You can take it as H, 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 H. Now if you just treat it with water in presence of H plus, you will get HNOH. Now it doesn't matter where this H and OH are going because it is a symmetrical alkene. Symmetrical alkene means if you just cut the double bond from middle, then both of the side will look identical. Just they are inverted. So this thing is inverted, right? So this is the meaning of symmetrical alkene. Now what will happen if we take an unsymmetrical alkene like this? So this is an unsymmetrical alkene. Why is it so? Because on the right side we have a CH2 group, but on the left side we have a CH3CH group. So the both sides we do not have identical group. Therefore it is a unsymmetrical alkene. Now unsymmetrical alkene has one problem, that now we have to decide where this OH and H will go. Initially in this case, if we add OH here or here, they will both result in the same product. Just you can try it, this practice at the home, or you can try this at home. Okay, just try to put OH here and see the product. After that, put the OH here and see the product. You will find that both of these are identical. Now this is the case of symmetrical alkene. Now what will happen if we take such unsymmetrical alkene? So for these things, or for these cases, we have something called Markovnikov's rule. We have used this earlier also when we are preparing our, say, halogen, or you can say halogen containing compound using an alkene. There we added halo acids, that is HX, where X was chlorine, bromine, iodine. So in that case, chlorine, bromine, iodine only. So in those cases, we followed the Markovnikov's rule. We will follow the same here also. So what is this Markovnikov's rule? It says that the negative part, so if we have an acid like say this is an H2O, okay, so it has a negative part and positive part. How? So if you just put it in the form of HX, so take an H out here, so what will be left? You will be left with OH. You can also write it as H plus and OH minus. Now this rule says that the negative part goes to that carbon. So this is the negative part. This is clear. Okay, so this is the negative part. You cannot put a negative charge on this H. So the negative part of this say substrate goes to that carbon which can form the most stable carbocation. Okay, so it goes to that carbon which can form the most stable carbocation. How? So if you see this thing, so two carbocations are possible from here. So make the carbocation like this. So first identify the double bond. Now identify both the carbons which are this and this. Now try making positive charge on both of this. Suppose I am putting positive charge here. Now H is attached. Now the one which is not getting your say this positive charge must be added with one H. Similarly, if you put the positive charge on the other carbon, you will get something like this. Here H, here CH3. Now I have told you that the one which is not getting the positive charge must get an additional hydrogen. Now compare the stability of these two carbocation. You can see very clearly that it is a secondary carbocation as two carbons are attached to it, but this is a primary carbocation. Now secondary carbocation has more number of alpha hydrogen. You can see that it can have 1, 2, 3, 4. Sorry, it will be So 1, 2, 3 from this carbon, and this has 1, 2, 3 here also. So 3 plus 3, 6 hydrogens are present. 6 alpha hydrogens are present, but here only 2 alpha hydrogens are present, that is 1 and 2. Now more number of alpha hydrogen means greater hyperconjugation. Greater hyperconjugation means greater stability. So you can just remember it directly also that tertiary is stable than secondary and secondary is stable than primary. So we will form the carbocation here only. Therefore the negative part will be attached to this carbon which is forming the stable carbocation. So you can see the result here also. So this is just a mnemonic device that you can use to directly interpret your product or directly look for your product. But if you go through the mechanism, it is not that much simpler. So it involves 3 steps. So we'll look at the mechanism. So be aware about it. So if you look at the book, your book will be mostly saying that the negative part will go there, which is more substituted. But this is not always the case. Okay, remember this thing that this is not always the case. So look for that carbocation which is more stable, not the one that is more substituted, which is more stable. For example, you have such a substrate like this. Okay, and suppose this is like this, and here. Now if you just add H plus, where it will go? First of all, look for the more electrophilic, you can say more electron density containing double bond. So you can see here that since it is more substituted, this one is more substituted, the more and more electrons will be donated to this double bond. So your H will go here. So how I am doing this? Because you know this H plus that is being added to it, so it is a kind of acting as a nucleophile, because it is attracting towards nucleophile, and this is acting as an electrophile because it is getting attracted to this is electron rich. Now the more electron rich will be reacted first, because this H plus is looking for electron. Okay, so more electron rich is this one, so I have substituted H here. Now 2 possibilities arise. First, the H goes here and we get this kind of carbocation, right? The second possibility is H goes here and we got this kind of carbocation. Now, according to your simple Markovnikov rule, the rule you must have seen twice or thrice, you must say that okay, this is the more substituted carbon, so the positive charge will be more stable here and the OH will attack here. Means directly you will attach the OH here, because you will say that this one is more substituted carbon, so the negative part will go to this, but instead OH will be attached here and not here. Now, why is it so? So, when you will look at the mechanism, you will see that a positive charge is being developed. That's why the more substituted statement is seen. But it is done for the deciding. It is done for deciding the stability of carbocation, and you can see it very clearly that it can do resonance. Okay, so since it can do resonance, so this kind of resonance is possible. And you know that hyperconjugation is more pronounced that say our hyperconjugation is less pronounced than resonance, because hyperconjugation is kind of partial shift of sigma bond, and this resonance is complete shift of pi electrons, and these are pi electrons, and they will show complete shifting. And more is the delocalization. Shifting means what? It is moving from one place to another, it is getting delocalized. So the more delocalized system or the more delocalized charge is more stable. Think of it like this. So suppose you are given a heavy thing, okay, something heavy, and now you are told to lift it up. Suppose it is of 20 kilos, and you are told to lift it up. You will find it difficult. Now suppose a person is given to you as aid, who will help you to carry this luggage. Now it will make your means efficiency more, because now two people are there, so they will be able to carry that charge more easily. So think of this as the same. So this is our charge, and it is a kind of burden only, because charge is something which is making this species unstable, because charge species are generally not stable until and unless it is neutral, because nature always tries to be neutral. Okay, so for this reason, what happens here? So this in this case, the positive charge is only stabilized on this center. But when you put the positive charge here, it is being stabilized by two centers. First, this carbon holds this positive charge, and sometimes this carbon. So you can just imagine it like that it is a kind of weight which is being distributed between two carbons, and hence it has become stable. Okay, and in hyperconjugation, if you just imagine it, you can find that okay, the charge is being delocalized, but the extent is less, because the breaking of sigma bond is not that much easier, so it does not move completely. But since resonance is the movement of pi bonds, so therefore there is complete movement of kind of, means you cannot say 100% complete, of course, but to a larger extent this charge is been delocalized as compared to hyperconjugation. Therefore you will find that this carbocation will form, and your negative charge will be coming here. So is this clear? So this is the funda, that you will not look for the more substituted carbon, you will look for the carbon which will form the more stable carbocation. So is this clear? Okay, so we are done with this thing. Now we'll see the mechanism. Why are we looking for the stability of carbocation? So the answer lies in the mechanism. So here is the mechanism for that. So this is our alkene. So we are just taking a general formula. We have not substituted this thing of all the four parts. Okay, right. Now, first of all, this reaction will happen. So do not get confused with this thing, because acid will never be present as H plus. Okay, we can use it sometimes for our mechanistic part, but in the real appearance, it always is present in this form. You will see for that I have used H plus also in some cases, but in reality this H plus never exists. You cannot say never exist, means most of the equilibrium are shifted on this part, means most of the H plus is present as H3O plus. Okay, because again the same funda, that it is delocalized, or you can say stabilized, because three hydrogens are there, so it is stabilized. So here are our species that is present in our aqueous system, that is H3O plus. Now this double bond, which is electron rich, will take this H, and we will get your carbocation here. Now you can see that this step is the first step, and let me make one thing clear, that this is the RDS. RDS means rate determining step, or the slowest step. Now this both things are similar. Not similar means this both thing goes hand in hand. If a step is the slowest step in that reaction mechanism, then that reaction, that step will be only the RDS. RDS means rate determining step, means the step that determines the overall rate of reaction or the speed of reaction, that how fast or how slow that reaction will go. So you must have seen this say your concept in chemical kinetics, where we see the RDS for deciding our order of reaction. Okay, now why is this slowest step called the RDS? You can think of this from your daily life. Suppose a relay race is being done. Now, suppose out of first, second, third, fourth, three runners are good at running. Their speed is good. Now, the fourth one is not that much efficient. He or she runs slowly as compared to three of them. And the difference is large. Okay, so suppose all the three are running at 21, 22 or 20, then the third one is running at 10 miles per hour. Okay, now the slowest one will be with the deciding factor, because if he runs faster, then it will decide the you can say result of the relay race. So therefore you can think of it that how this RDS is, in the similar analogy, is deciding the rate of reaction. Hence this is the RDS. Therefore the stability of carbocation is more important, because more stable is the carbocation, more faster this reaction will go. Now once the carbocation is formed, the H2O that has been formed here, this one, it will attack here. Okay, so this will form this kind of species. Now since oxygen has donated electron, this oxygen will bear a positive charge. Again, since we have said that this is an acid catalyzed reaction and the species that was deployed in the starting, it is H3O plus, so we must get this back. Now the H2O, another H2O will come. Okay, another H2O will come and take this H, and you will again get back this H3O plus, which was employed firstly. Okay, you can see that it has been reverted back and we got our product. Now in this whole mechanism, three steps are occurring. First, the protonation is taking place. Okay, the alkene is getting protonated. Second, the nucleophilic attack of water is taking place. And third, the deprotonation of alcohol is taking place, and we get our final alcohol. And the thing that you should remember is that this is the RDS. This is the RDS. So the stability of carbocation will decide the overall rate of reaction. Is this clear? Okay. Now we'll move to the next way in which we can form our alcohol using alkene, that is hydroboration oxidation. Hydroboration oxidation. So in hydroboration oxidation, we use diborane, that is BH3 whole twice. So it can be written in this way also: BH2 and one more H, that is 3, BH3 whole twice. So it reacts with alkene to give trialkyl boranes. So this is the trialkyl borane. Now upon hydrolysis of this, we get our alcohol. That is a different thing. But for now, consider this reaction. So we are adding HBH2 to this alkene to get our trialkyl borane, which is the addition product. Now this trialkyl borane is oxidized to alcohol by hydrogen peroxide. So this is the hydrogen peroxide, H2O2, in the presence of aqueous sodium hydroxide. Aqueous sodium is hydroxide. So at first sight, this reaction looks complicated, but when you get used to its mechanism, you will find that, okay, this is not that much complicated, right? Now, what are the things that is to be noticed here in this reaction? First of all, you can see that here, this has two parts. Again, I am dividing it as, suppose, our thing, that is, say, negative and positive part, in which H is the positive and BH2 is the negative part. But what happens here is that this BH2 is not getting added to your more stable carbocation. Instead, it is getting added to the less stable carbocation, or less substituted, you can say also. But what is the reason behind it? So the reason will get clear in this next mechanism. But for now, assume that, okay, this HBH2 addition, only HBH2, I'm not talking about OH right now. HBH2 addition takes place in opposite of, means in the opposite direction the Markovnikov predicts. So if Markovnikov predicts that the negative part should go here, Then if we do the hydroboration oxidation, the BH2 part will go here. So, and one more thing, here 3 moles are required. So first this 1 mole adds, okay, then again this 1 mole adds, then again we react it with the second mole of this alkene, then the second mole add, then we again react with the third mole of alkene, then the third mole add. So you can see that now this whole thing has a coefficient that is 3 outside here. So 3 alkyl chains have been added to the borane. You know that borane can form 3 bonds. Now each of this H is replaced one by one, and we got this thing finally. At last we have done the oxidation and we got our propanol. So the addition of borane to the double bond takes place in such a manner that the borane gets attached to the sp2 carbon carrying greater number of hydrogen atom. Okay, so this is a general statement. Again, look for, here do not look for the stable or unstable carbocation, look for less sterically hindered carbon. Okay, less sterically hindered carbon will get our BH2. So what is the reason behind it? We'll get to that. But for now, think of it that the BH2 will be added to that carbon which is less sterically hindered. Now this carbon has already one CH3 attached to it and one H, so it is more sterically hindered due to presence of this CH3. Instead, it will add to this one which has only hydrogens as it is substituent. Okay, therefore BH2 adds here. Now the alcohol so formed looks as it is has been formed by the addition of water to the alkene in a way opposite to the Markovnikov rule. Okay, so it may look like at the first that okay, if it was your simple H2 addition in the presence of acid, then OH would be added here, but instead it is added here, so it is kind of anti-Markovnikov rule. But remember, this will always not be followed. So remember the basics. So in case you are adding in the presence of water acid catalyzed, look for the more stable carbocation. There the negative part will go. If you are doing the hydroboration oxidation, look for carbon which is less sterically hindered. So we will look at its mechanism to get the idea why is it so. So here is our mechanism. So you can look here that there is in this mechanism there is no such formation of your carbocation. It is just a concerted mechanism. Concerted mechanism means what? Addition and you can say both the bonds, addition and breaking of bonds are occurring at same time, similar to our SN2 reaction, in which we said that the bond breaking and bond forming both take place at the same time. Therefore we get this kind of transition state. So these two bonds are formed. Okay, these two bonds are formed, the shown with dotted. This alkene bond has been destroyed, it is also shown as dotted, and this bond has also been destroyed. Okay, so 2 sigma bonds have been formed, 1 pi and 1 sigma is been broken, and we get a concerted mechanism here, and this is our transition state. There 2 bonds are breaking. So let me show the breaking one with red one. So these 2 bonds are breaking, the pi bond and the sigma bond between B and H, and these 2 bonds are been formed. That is the bond between carbon boron and carbon hydrogen. So we finally get this. Okay, is this clear? Now if you do the oxidative addition of this one, you will simply end up with removing this BH2. Okay, but usually it does not happen now because this substrate is present always in excess. The same thing, this thing will happen with this BH bond also. Okay, this BH bond also will go through the same transition state. Similarly, this BH bond will also go through the same transition state. At last, just we will oxidize this thing and get our OH here. So the thing that is to be noticed here is that since it is happening concentratedly, that is the attack is happening concentratedly, there is no formation of intermediate carbocation. Therefore, it simply follows the rule of steric hindrance. Less is the sterically hindered your carbon, the BH2 will attack to that carbon only. Clear? Now, if you look at the HOMO-LUMO level, so I will not get through all the technicalities. So let me remove this HOMO-LUMO and simply call them as orbital. So first, this and this orbital will be formed, will be overlapped. Okay, and secondly, this bond will be donated to this anti-bonding part, which is now vacant, and this will result in this also. but it is just to show the things in a more simpler way. Actually, the things goes like this, where we have a transit state due to concerted mechanism. So this were the two methods that can be used for the preparation of your alcohol using alkene. Now we will use the aldehyde and ketone, that is the carbonyl compound, to prepare our alcohol. So how it can be done? So it can be done by the reduction of the corresponding alcohol. Okay, reduction of the aldehyde and ketone to the corresponding alcohol. How? By the addition of hydrogen. So you can see that O has been remained, but 2H has been added. So one H is here, H2, and one H2 your O. Okay. So this is the addition of hydrogen in the presence of catalyst, that is catalytic hydrogen. Because we have used PD here, so it is done in the presence of catalytic hydrogen. The usual catalyst is a finely divided metal such as platinum, palladium, or nickel. So why do we use this finely divided? What is the meaning of this? So finely divided means it has been converted to smaller parts, smaller cubes. Suppose we have a large cube, then we break it and convert it into smaller cubes. And why is it done so? To increase the surface area. Okay, so more is the number of particles, more will the surface area. You can just take a break and think of it that, okay, we have a large cube. Now we broke it into smaller parts. Then you will find that the surface area will increase. Just try to do it by your, say, all the area finding methods, and you will find it. Just take a cube, take it of any length. Now divide it in equal parts. Okay, now you measure the surface area of the initial one and the resultant one. You will find that, okay, the resultant one has more surface area. Now no more surface area means more of the RCHO can be attached to it, and your H2 can be attached to it. Therefore it will result in greater amount of product. So this is the first method. The second method is by treating your, say, this carbonyl compound with, or ketone with, your NaBH4. This is a reducing agent, that is NaBH4, and its structure looks like this. So since it has an extra electron here, so it will look like this, Na plus and BH4 minus. Now this H is donated on this carbonyl. So it is simply a nucleophilic addition. So we'll see to it what is nucleophilic addition, but let me just give a glimpse of it. Suppose this is our ketone, this ketone is here. Now this H, BH4 minus H, will go and attack here. Okay, it will attack here. This charge will go here. Now since we have H plus present in the solution, this O negative charge is further neutralized, and we get this RCHOR. So we'll get to this nucleophilic addition in the later on classes when we will study aldehyde, ketone, carboxylic acid. But for now, just think of it as a simple attack where a BH4 minus H hydride, it is a hydride donor. This NaBH4 minus is a hydride donor. What is hydride? H minus species is called as hydride. So NaBH4 H minus or hydride is been donated to this carbonyl compound, and it is being reduced to your secondary ketone, secondary alcohol. Now you can remember this thing also, that aldehyde results in the production of primary alcohol and ketone results in the production of secondary alcohol. Okay, clear? Now next we can reduce this carboxylic acid also to get our carboxylic acid and ester, both we can reduce to get our alcohol. So how can we do this? So for this we'll use another reagent, that is LiLH4 instead of NaBH4. Now what is the reason we are using this LiLH4? This is a stronger reducing agent as compared to NaBH4, and the reason why we are using this is that, so we'll study in the next chapter also, but let me give a small description here, that okay, this carbonyl center is simply an attack of this reduction is simply an attack of H minus, that is our nucleophile, on the carbonyl center, which where the carbon that is attached to double bond oxygen is carrying a positive charge, so it will be electrophile. So attack of a nucleophile on an electrophile. Now since this kind of bond is formed in case of carboxylic acid. Due to the donation of this lone pair on between carbon, you will get this kind of resonance, resulting in less polarity of this bond. So this delta positive decreases because of donation from this oxygen. Hence, we require a stronger reducing agent like LiLH4 to reduce our carboxylic acid and to get our alcohol. Now here also you can see that this carboxylic acid is reduced to primary alcohol. Okay, this is clear. But this LiLH4 is an expensive reagent, therefore used for preparation of special chemicals only. Now, how do we do it commercially? So this LiLH4 is very expensive, so we do not use this same method on an industrial scale. So for this kind of industrial application, we first convert this acid into ester by esterification using alcohol. So we esterify this, say our carboxylic acid to get a RCOOR-. Then this thing is further catalyst. You have been using catalyst. It has been reduced to alcohol. That is this one. Plus this R-OH is also formed. Now the question asked here is that why is it happening in this way? So for that you have to be looking at the mechanism. Okay, so we'll look at the mechanism of all of this reduction of carboxylic and aldehyde and ketone in the next class, in which we will study aldehyde, ketones and carboxylic acid, or you can say in the next lecture series. So we are done with this carbonyl. Now we'll move to Grignard reagent. Okay, so how can we prepare it using Grignard reagent? So alcohol are produced by the reaction of Grignard reagent with aldehydes and ketones. Now how it happens? Again, it is the nucleophilic addition. So if you remember, we have prepared this Grignard reagent using our alkyl halide, in which we simply treated our alkyl halide in presence of Na and dry ether with Mg to get our RMgCl. So this is the same thing here. Only here we have put X, so X can be chlorine bromine, right? Now what we do, we look at this bond. So if you look at this bond, this Mg is of course a greater positive charge carrier because it is electropositive nature. Therefore this R will be negative. Okay, and it will carry a delta negative charge. Now this oxygen is electronegative, so it will also be a positive charge center. Now this negative part of this R attacks on this carbon, which is carrying a positive charge. It will move, and this bond will move here. So it is very important to get an understanding of this arrow pushing mechanism. So this tail is representing your the source of electron, and the head is representing the area where the electron will be donated. Here also, this is the tail. It will locate our electron source, which is the pi bond, and this is the oxygen where the head is gone, is the electron acceptor. Now since this pi bond moved to this oxygen alone, it will get a negative charge, which will be stabilized by the Mgx, because this now both of these bonded electron are be taken by R. Therefore this Mg will have a positive charge, and this kind of adduct will form. Now you do the hydrolysis of it and you will get this thing. Okay, is this clear? And plus we get your MgOH2x. Now this is the way in which we can prepare alcohol using Grignard reagent. Here also we have used carbonyl compound also as our substrate, you can say that, but the main role is being played by your Grignard reagent. And you must also remember the method by which this Grignard reagent is prepared, because that indirectly this question can be asked. The first you may be asked to prepare your Grignard reagent, and further by using that on your carbonyl compound, you may be asked that okay, now predict the product. So let us look at some examples here for Grignard reagent. Suppose we use a simple formaldehyde. Then in that case, we will get our RCH2OH. This R again attacks here on this carbon, and we get our RCH2OH. Now suppose we use a greater aldehyde, or you can say something that some aldehyde that is having a carbon on the left side. Again, now this R dash will attack. Now this will result in a secondary alcohol. Okay, the first formaldehyde was resulting in a primary alcohol. Thus here it is resulting in a secondary alcohol. Now let us use a ketone. So ketone, now third alkyl group will add, and it will result in a 3-degree alcohol. So it is 2 degree. So let me write it. It is, use a different pen. Okay, so it is 1 degree alcohol. This is 2 degree alcohol. This is 3 degree alcohol. Now we can make a general statement: the reaction with a primary alcohol with methanol. Okay, reaction produces a primary alcohol with methanol, secondary alcohol with aldehyde. So if you use any aldehyde, you will get a secondary alcohol only. And if you use a ketone, you will always get a tertiary alcohol. So you should remember these 3 things. So if we use a methanol, then you will get a primary alcohol. If we use a aldehyde, we will get a secondary alcohol. And if we use a ketone, we will get a tertiary alcohol. So this is the way, some examples of a Grignard reagent. Now I would like to put up one more this example. So it is a rearrangement reaction. So it is very good practice to see such complicated reactions. So because this type of questions are only asked in JEE, where you have to rearrange the carbocation to get the most stable one species, to get the most stable species. So here is our question. Suppose you are given with this starting substrate and you are told, okay, do the acid catalyzed reaction of this. So first of all, it is acid catalyzed. This H plus will go here. Now 2 possibilities occur here. First, that this H plus goes here and positive charge occurs on this place, which is being shown here. Second case can be that our H goes here and positive charge builds up here. But since this is the positive, this is a primary carbocation and it has no allylic backup, therefore it will not be formed, because this one will be more stable carbocation as it is a secondary carbocation. Now the simple mistake that can be done, or it will be done only because we do not think of it twice, that okay, this is the center, we will directly attack our OH and you will get here our OH. But this is not the case. Now there is a possibility of methyl shift. This is our methyl group. Now this can be shifted from here to here. So there will be a rearrangement. The methyl will move from here and will be attached here. Now since methyl takes the electron pair along with it, we will again get a positive charge here. Now this positive charge, this carbocation is tertiary carbocation. So this is the driving factor behind the movement of this methyl from here to here. Now let me make it clear that okay, 1,2 methyl shift is somewhat common, but 1,3, 1,4, they are not that much common. They require a special configuration. So we'll not see that example. You can just consider a 1,2 methyl shift. What is 1,2 methyl shift? 1,2 means this is one position and the second carbon just adjacent to it donates it alkyl group. So this is possible. And plus you will have to require a special configuration. Suppose a carbon is present here that has an alkyl group, but the possibility of this moving here to here is very less. We will not encounter the example, I think so. So therefore this methyl shifts here and we get a positive charge here. Now at this point OH will attack and you will get a product. Okay, so 2 types of dilemma occur here. First of all, where the H will go, where the positive charge will be stable, here or here. Okay, we find that okay, this is secondary carbocation, so here it will be stable. Now we will simply say that OH will attack here. No. Why it will not attack here? Because there is a chance of migration of this alkyl group, so it will migrate here to form a more stable carbocation. At last the OH will attack here. So you can think it is a very good example. Okay, so you must practice it by yourself also. You must try this rearrangement type of reaction by yourself so that you can get a more good idea about it. So in this ways we can prepare our alcohol from various substrate. Like first we have used our alkene. Okay, first we have used our alkene where you use our hydroboration oxidation and acid catalyzed reaction. In acid catalyzed reaction, the negative part of our addendum will go to that part which forms the more stable carbocation. That is the Markovnikov's rule. Now, in case of hydroboration oxidation, the negative part goes to that carbon which is less sterically hindered, and it is termed as anti-Markovnikov's type of addition. And one more thing it is to be noticed that there was that the trialkyl boron formation. So each of the hydrogen of boron will be replaced one by one, and that replacement will go through transition state formation. Means both attack, or you can say both formation and breaking of bond occurs at the same time. After that, we move the preparation that was based on aldehyde, ketones, and carboxylic acid. For aldehydes and ketones, we can either use the catalytic hydrogenation, or we can use some reducing agent like NaBH4. We can also use LiLH4 also. There is no problem in it. You can simply use LiLH4 in place of NaBH4, no problem, because it is a stronger reducing agent. But since it is an expensive one, then I would suggest that NaBH4 is the more appropriate one. Then we move to carboxylic acid. So carboxylic acid can be reduced to your alcohol in two ways. First way was that you simply use a stronger reducing agent like LiLH4. But since it is expensive, therefore what we will do first, we will esterify it using an alcohol. Once it is esterified, reduce it using your catalytic hydrogenation method. Okay, so this was the way your carboxylic acid and ester can be reduced. Now the next one was Grignard reagent. So for Grignard reagent, one point should be very clear, that okay, you should have a proper idea that how this Grignard reagent can be prepared. So it is simply prepared by reacting our alkyl halide with magnesium in presence of Na and ether. So you will get a RMgX. Now what are the things that is to be noticed here? That is RMgX has two parts. One is R, that will carry a negative charge, that is the negative part, and this MgX is the positive part. Now this R, which is having a negative charge, it will attack the carbonyl, which has a nucleophilic center, or where there is a positive charge on carbon, delta positive charge. This R will attack here and the alcohol will form. Now the three cases arises here. The cases are: first, if there is attack on methanol, primary alcohol will form. If there is attack on aldehyde, secondary alcohol will form. And if there is attack on your, say, ketone, then a tertiary alcohol will form. But there is no such mention of your carboxylic acid. You cannot use this carboxylic acid along with a Grignard reagent to give this your product, or to give this alcohol. Now why is it so? Here the question stops at one thing, whether this RCOOH will give nucleophilic addition, or you can say nucleophilic reaction, or acid base reaction. Now by name, or you can say it also, that since RCOO minus, that is the format, or you can say the carboxylate ion is stable, therefore there is a chance of acid base reaction, and RMgX is a good base also. Okay, it can act as a base. So for that cases, what happens, this RCOOH, if you react it with any, say, Grignard reagent, it will result in simply this thing. Okay, you will get a acid base reaction. Okay, so you cannot use this method. You cannot use this carboxylic acid for the preparation of your alcohol, because it results in a acid base reaction rather than a nucleophilic addition. Okay, this is clear. At last we have seen example that you can just look at it again, and you can just sum up similar examples to it. So thank you for today's time. This was for today's lecture. So tomorrow we will be starting with this phenol. We will see the classification. So we have seen the classification, I think. Now we will move to your preparation of methods of phenol. So since this phenol is different in nature, the CO bond, it is between the carbon and the oxygen. In case of phenol, are different. So some different ideas has to be employed to prepare those phenols. Okay, this is clear. So thank you for today's time. Thank you.